Hello everyone, this is Hassan. Today I'm going to present on the structural constraint and motion analysis of lower DOF parallel manipulators, taking 3 PRS mechanism as a demonstrating example. First, I will introduce the basics, define the problem, and present the proposed approach. Then the constraint analysis and rate kinematics will be discussed as the basis for the parasitic motion analysis. Following the rate kinematic analysis, the parasitic motion handling will be discussed at the velocity level and concluded. Talking about parallel manipulators, the general parallel manipulators have all motions in space. However, if the parallel manipulator is constrained, there are some space that the moving plane cannot reach. Therefore, the general space will be decomposed to free motion space and constraint space. In order to have a full kinematic information of the manipulator, we need to consider both the constraint and free motion spaces. Here is the general inverse rate kinematics equation. We have a joint rate, inverse Jacobian, and constraint compatible task velocity. For some lower DOF parallel manipulators, x dot, the constraint compatible task velocity, is not only the degree of freedom of the manipulator, but also the parasitic motion. Parasitic motions are dependent motions that occur in the direction of the restriction space. Previously, researchers tried to handle the parasitic motion by analyzing the constraint at the position level. So the parasitic terms are expressed as a function of free terms. Since most parallel manipulators control scheme is velocity level, the time derivative of position level relation is used to solve the rate kinematic. If the optimization is required, the position level relation will be used to remove the parasitic motion from the workspace. However, we think this approach has some drawbacks. The first drawback is it's entirely geometric dependent and cannot be consistently applied to several manipulators. The other drawback is the approach is not straightforward with the common control scheme of parallel manipulators. The third drawback is the approach cannot be used to identify the parasitic terms from the free terms. In order to establish the coupling relation by expressing the parasitic term as a function of free terms, we have to identify what terms of x are the parasite and the free terms. Considering these drawbacks, we proposed entirely velocity level approach. First, we analyze the limb motion at the velocity level and obtain inverse Jacobian of the manipulator. The inverse Jacobian comprises the actuation and constraint ranges. To get a constraint compatible task motion, we project the constraint information of the manipulator onto its null space. Then we use the constraint compatible task velocity to solve the inverse rate kinematics. Moreover, we use this information to identify the parasitic terms and independent terms in x dot. After we obtain the velocity level constraint compatible motion, we can obtain the position information by integrating the x dot. This is the example manipulator we use to demonstrate the approach. Our approach starts by isolating the limb from the manipulator so that all the relations will be obtained first at the limb level in the limb frame. In order to analyze the limb motion and constraint, we use the instantaneous motion space and instantaneous restriction space concepts, which is proposed in this paper. To analyze the instantaneous motion space and instantaneous restriction space, we use the screw theory. Motions and constraints will be represented in screw, which is a 6-dimensional spatial vector. And to get the constraint from the motion screws, we use the reciprocity relation like this. For the example manipulator, the limb IMS and limb IRS is obtained from the isolated branch. And the isolated branch have the local frame, and all the limbs screws will be represented in this local frame. For this isolated PRS limb, we will have 5 screws, one infinite pitch screw and 4 zero pitch screws that represent the revolute joint and spherical joint. From this limb IMS, we obtain the limb restriction screw. From the reciprocal screw, we get the direction vector for the limb restriction screw, and simplifying this will give us this vector, and further simplification of this relation gives the direction vector for the limb restriction is along the direction of the revolute joint. And also the moment vector is obtained as a zero vector. Once we have the limb restriction screw, we append that into the limb motion to get the extended Jacobian. And after obtaining extended Jacobian, the active range screws will be obtained by using the reciprocal screw relations. So that we obtain the active range screws in the local frame, and also we obtain the passive joint screws similarly. By using the elliptic polarity of the limb restriction screw, we obtain the limb constraint. Since all the relations so far are represented in the local frame, we need to use a screw transformation to represent it in the manipulator level. So we use this relation to transform all screws in the fixed frame, and ranges are also represented in the fixed frame. After transformation, we obtain inverse rate kinematic relation. This is the active joint velocity, passive joint velocity, and constraint. And x dot is the constraint compatible task velocity. It should satisfy this constraint relation. But how can we find x dot from the structural constraint information? Here is the solution. By projecting the constraint matrix onto its null space, we obtain the constraint compatible velocity. So for any user input or any arbitrary velocity x dot a, we obtain constraint compatible motion x dot. And as we said, x dot comprises parasitic terms and independent terms. We don't know at this level, but by using this information, we can find or reveal what terms are the parasite and what terms are the independent term of the task space. In order to do that, set the manipulator at the home configuration, which is both the moving plate and base plate are parallel. At that pose, the projection matrix will have this form, and any input Vx, Vy on the right-hand side will not produce any non-zero values at the x dot. Similarly, Wz will not produce any non-zero value x dot. So that when we give Vx, Vy, and Wz at the home configuration, there will be no motion to the manipulator. However, if we give either of these three terms to the manipulator or all of these terms to the manipulator will start moving. In that case, we identify that Vz, Wx, and Wy are independent, while the others that do not generate any motion are the parasitic terms. For verification, we can also compute the forward kinematics and to get x dot, so that we can use this information for comparison. In order to get the joint value, we can integrate the joint velocity by using an accurate numerical integrator such as RK. After obtaining the joint value, we can compute the forward kinematics. For the reference pose, we can integrate the constraint compatible task velocity to get the reference pose. The linear term can be easily integrated, but the angular term requires the quaternion relation. In order to solve the example manipulator, we use this geometric information. First, give all the angular terms to x dot a and filter that. This is x dot a, and filter that with the projection matrix to get this constraint compatible motion. The constraint compatible motion shows the parasitic terms Vx, Vy, and Wz, and the remaining terms are independent terms. And with this constraint compatible task velocity, we obtain the leg velocity. So this is the leg, the active joint velocity for the three legs, and this is for the passive joint velocity below the moving platform. And as can be seen, the constraint is perfectly satisfied. For comparison, the forward kinematics is computed, and the result is similar with the reference pose, the reference velocity. By integrating, we can obtain the desired moving platform pose, and by computing the forward kinematics, we get the forward moving plate center, so that we have the reference and computed or desired moving plate center. Similarly for the orientation and the reference passive joint and the computed passive joint are also obtained. The leg lengths are computed. All this will be used to compare. The comparison shows that the simulation error is in the desired limit. In conclusion, the rate kinematics in this study is obtained, and position relation are derived from the velocity relation in a consistent manner. The strange kinematic behavior called parasitic motion is described without any explicit position level parasitic motion, so it greatly simplifies the task planning procedure. The method also used to identify the parasitic terms from the main term. The exactness of the approach is also shown by taking the difference between the reference and the computed results. Thank you very much.